1 chapter, and let me know if you don't, because this is a brand new version of Wiley Plus, which means I'm still kind of making the occasional mistake in that oftentimes I think you're looking at something that it turns out you're not looking at. So that's why it's all my fault. And it's just my lack of familiarity thus far with the current version of Wiley Plus. This is our first chapter 9 problem. The homework that's due on Sunday is, I think it's only 10 prompts. So that's kind of on the lightweight side, which is good because it's an exam week. So, we don't need a heavy homework assignment on top of an exam, but we can't stop. We can't rest on our laurels. We have to keep going forward. And I said this multiple times. Basically, the foundation is motion, force, work, and energy. Motion, force, work, and energy. You studied motion in chapters 2 and chapter 4. You studied force in chapter 5 and chapter 6. You studied work in chapter 7, and sort of, again, chapter 7 for energy and chapter 8. So this is, I consider this to be the foundation. I think of this as the foundation on top of which everything else rests. So there's the foundation, and on top of the foundation, you have everything else. So for example, we have momentum, and hopefully, just in case, let me just reference this. As you saw, I think, there is no chapter 9 green sheet lecture. There's only some images. So everyone here has the chapter 9 green sheets. There's no lecture video you watch. Instead of watching a lecture video, you just go into this folder that I made available, and you click yourself through these images, and this is how you'll fill in the green sheets using this method. And just always remember, this is a great opportunity. The chore that you have to go through to fill in your green sheets by basically copying off this image set or video is great, because that's a great opportunity for you to say, okay, I'm writing this down, but what the heck does that mean? Just be constantly skeptical, constantly, suspicious about everything you're writing down, meaning like, I don't want to be writing down something that I don't really understand. So just have that kind of, side eye type of view on everything you write down. So that's what I wanted to mention about chapter 9 green sheets. Okay, so here's our first. So as mentioned, now that we have the foundation established, this chapter is nothing more than momentum equals, momentum is equal to mass times velocity. And on top of that, we have something known as impulse. And it turns out impulse can be represented as this integral. And it turns out that this integral is also equivalent to the change in momentum. And let's see, I guess and then collisions, and then just 3 collision types. Collisions. So in a nutshell, I'm boiling this down dramatically, but this is the essence of this chapter. Collision, there's perfectly elastic, meaning 2 objects bounce off each other with no loss whatsoever in kinetic energy. There's perfectly inelastic, which means 2 objects collide with each other and they stick together like 2 blobs of clay, perfectly inelastic. And the third category is basically just called elastic, which is somewhere in between. It's not perfectly elastic. It's not perfectly inelastic. There is some energy loss. Perfectly, or just elastic. All right, that's it. So the other thing that I'm not drawing a lot of attention to, which I kind of maybe should, I don't, just because sometimes you just got to do triage, is this whole center of mass conversation. So I include center of mass content in your lecture notes, but I don't really directly address it here because I don't think it's incredibly challenging. But having said that, just because it's not incredibly challenging doesn't mean it's not essential. So just wanted to provide the content for that without spending any airtime on it. In this situation, we have a super ball bouncing off a wall. It says the figure, this graph is an approximate plot of force magnitude, of magnitude F versus collision time of a super ball bouncing off a wall. So I'm going to draw a wall. Here is a wall. And here is a, wait for it. I think I got to restart. Let me restart, stop. Okay. Try that again then. Here's another attempt at a wall. Here's a super ball. Got to be careful. It's the initial velocity of the ball is 35 meters per second perpendicular to the wall in the negative X direction. So here's my super ball, and it's heading in the negative X direction, like this, with a velocity, I guess I'll call it initial, with an initial X velocity still dedicated to subscripts. Vxi equals negative 35 meters per second. Those are my numbers. Then it says it rebounds directly back with approximately the same speed. So the ball makes a collision with the wall, and then it rebounds backward like you would expect. So the top is basically the incoming, and then the bottom is I'm showing my super ball bouncing off in the opposite direction with the same speed. And that's actually noteworthy. The fact that it's bouncing off with the same speed, this is Vx final equals plus 35 meters per second. So you know what that means. If my incoming speed is 35 meters per second, and my outgoing speed is 35 meters per second. You know what that means? This is a perfectly elastic collision, perfectly elastic. And this is what perfectly elastic means. It means the following. There's no change in momentum. Okay. Well, actually, let me just, there's no change in kinetic energy. I better say that. There's no change in kinetic energy, no energy loss. So this reminds you of energy analysis when we worry about non-conservative work, or we worry about non-conservative forces doing non-conservative work, either adding or stealing energy. So it's still barking up that tree. There's no energy loss in this collision. Normally, and that's theoretically, practically speaking, normally you would have heat. If this super ball was colliding with the wall, you would lose heat, you would lose energy to heat and sound. But we're ignoring these losses now and considering this to be a perfectly elastic collision. The question now is, what's this variable? It says, what is F max? And imagine how important finding this out is to you as a scientist or engineer. You need to know the maximum force. And why is that important? Because you need to design for this type of performance. What if I have a super ball? Let's just, well, here. Apparently, my super ball is experiencing a F max force. Apparently, the maximum force acting on my super ball is 1,090 newtons. What if that broke? What if it caused my super ball to catastrophically fail? My super ball is made out of material that just can't withstand that kind of force, and all of a sudden the manufacturer is selling thousands of super balls that are crumbling very quickly. That's because you have a material issue. So knowing what the maximum force could be helps you design accordingly. So I would say, well, as a materials engineer, I'm going to formulate a material that can withstand this maximum force. And that's just a silly little example pertaining to the Super Bowl. Obviously, in automotive engineering, that comes first to my mind. Like if your car, if you get involved in a fender bender, a low speed accident, what is the impact speed that, what is the impact force that your head would experience if it collides with the steering column? And that's why you have airbags. And even airbags are problematic because sometimes an airbag works so well that the force that it exerts, the force exerted on your head by the airbag to keep your head from colliding with the steering column itself causes damage. And that was a long painful history figuring out how to engineer these airbags correctly. So we need to figure out this maximum force for lots of reasons. So I'm going to do this. I'm going to say, well, I know about the impulse momentum theorem. I know about that. Why do I know about the impulse momentum theorem? Because I checked out the downloadable lecture notes theorem. That's why. Well, I know about the impulse momentum theorem. Here is the impulse momentum theorem. J, vector J is equal to the integral of f dt. And it turns out that that's also equal to delta P. So this is the very first thing I'm thinking of because I need to find out what this maximum collision force is. So that just automatically makes me think of this. This is where I find my dollar sign. And let's see how applicable. Let's see how far I can get with the impulse momentum theorem. One thing I'll say right now, and you guys know about this, is I do know that about this integral. I have taken calculus before, and I do know that this equals the area under a force versus time graph. That's the other reason. I mean, I was given a force versus time graph, so that's the other reason I thought of impulse momentum theorem. Area under a force versus time graph. All right, so I'm going to run with that because I have a simple graph. All I need to do is figure out what the area under this curve is. And what kind of curve do I have? It's called a trapezoid. So I'm just going to spend some time remembering how to figure out the area of a trapezoid. And you don't have to memorize that. If you were doing this problem on exam 2 or exam 3, and you didn't know the area of a trapezoid, you would just ask me, and I would tell you. Although the area of a trapezoid is given to you on your exam sheet, you know, there's a list of formulas and stuff, constants on every exam sheet, and that does include the area of a trapezoid. Here's the area of a trapezoid. The area of the trapezoid is 1/2 h1 plus h2 times base. All right, so let's define what's h1. Let me clear the decks. And if you didn't want to deal with a trapezoid, you could just say, well, this is nothing other than 2 triangles and a rectangle. And that's even easier. But in the case of a trapezoid, let's talk about what is h1. This is h1 from here to there. There's h1. There's h2. This is h1. This is h2. And the base, here's the base of this trapezoid. And I just have, you know, I've worked with trapezoids enough so that I can remember this. But if you didn't remember this, or again, if you didn't like this, just call it 2 triangles and a rectangle. All right, but that's it. That's h1. That's h2. This is the base. And your thing, is that really the base? That looks like the height, but basically the heights are the 2 different parallel sides of a trapezoid. All right, so I have 1/2 times h1. H1, this is where you have to read the fine print. H1 right here is from 0 to 6 milliseconds. So 6 milliseconds is 6e minus 3 seconds plus H2. H2 starts at 2 milliseconds and ends at 4 milliseconds. So H2 begins at 2 milliseconds, terminates at 4 milliseconds. So that is 2 milliseconds. 2e minus 3 seconds. So that's H1 plus H2 times the base and the base. And finally, I see it. My base is F max. There's my dollar sign. Great success. Whatever this area is, because remember, this is the area of a trapezoid, and it does equal change in momentum right here. So again, I am living completely within the impulse momentum theorem, because here's my area under the curve, area of a trapezoid, and the impulse momentum theorem says that equals change in momentum. And you know by now, change in momentum, I'll go up here. Change in momentum is just final momentum minus initial momentum. I'm going to drop the vector symbol because if I'm just constraining myself to one dimension, I don't really have to worry about vectors, writing this as a vector. I can just deal with magnitudes. I would have to deal with vectors if I have 2 or 3 dimensions, right? So you know momentum, change in momentum is final minus initial. This is the basic introduction of chapter 9. Momentum is mass times final velocity. That's my final momentum. Here's my initial momentum, mass times initial velocity. And if I factor out a common term, I have mass times VXF minus VXI. All right, so here's delta P. Mass times VXF minus VXI. So we know everything except for the dollar sign. There's your dollar sign. What's VXF? VXF is plus 35 meters per second. What's VXI? Negative 35 meters per second. So it's a minus of a minus. So I have plus 35 meters per second minus a minus 35. And you can look at that. So if I have 35 meters per second going to the left and I end up with 35 meters per second going to the right, my change in velocity is going to be 70 meters per second. So just be aware of, again, you do have a minus of a minus. And when you solve for F max, you will get the right answer. And we just have to talk about units. F max equals 844e minus 3 do I know the math? 62 grams. So convert from grams to kilograms divided by okay, I actually get 1085. So Wiley Plus is showing 1090 because Wiley Plus is not, Wiley Plus every now and then I think adheres to sig figs, whereas most times they just want you to keep all the precision. That's where I get it from. And let's see, the units would be, the units, I got to do dimensional analysis. Getting the numbers the easy part, but we have to do dimensional analysis. So over here on the left side, I'm going to have seconds times force equals kilograms times meters per second. So that means that force variable, F max, the units for F max, I'm expecting newtons. Do I get newtons? Well, I would have kilograms on the right side, kilograms times meters per second squared. Yes, this is newtons. Dimensional analysis tells me I end up with newtons. And that is a tremendously helpful chore to undertake. You have no idea how many times I do dimensional analysis and I don't get the right units. And then I have to go back and kind of revisit my work. And, oh yeah, there's my mistake. So the units would be newtons. So this is our very first momentum problem, which is it's in generally this is a momentum problem. Specifically, it's a collision problem. And if it's a collision problem, then one of the first thing that pops into your head is impulse momentum theorem. All right, we'll get quiz 2 ready. Here's quiz 2. Chapter 9, quiz 2. Give me a second. All right, you should now see it. Our next momentum problem, chapter 9, quiz 2, should look like this if I've played my cards right. Okay. Another collision. This is another collision. So I'm thinking of all the collision stuff. But let's do the read through. We have a spring mass system. This is the expression. Whenever you have a spring attached, here's a spring. Whenever you have a spring attached to a mass, M for mass, K for the spring stiffness constant. Whenever you have a mass connected to a spring, that term is called spring mass. This is a spring mass system. You're looking at a spring mass system where block 2, which I know the mass, is at rest. So that's the mass of block 2 is meaningful. Sitting there at rest is meaningful. Frictionless is meaningful. Frictionless means no energy losses. Okay, so block 2 is sitting there minding its own business, and then out of the blue, block 1 comes sliding in from the left side and makes contact with block 2. And when they make contact, they stick together. So this is very important because if they stick together, that tells me what kind of collision. This is a perfectly inelastic collision, perfectly inelastic. Again, just think of two balls of clay, perfectly inelastic. Or think of 2 gigantic trains that couple. So I don't know if you've ever seen it, but there's a coupling mechanism. So when a train engine is sort of attaching itself to its load cars, there's a coupling that takes place. So it's like just these clamps that grab onto each other. This is a perfectly inelastic collision. All right, and then the question is, when the blocks momentarily stop, how much spring compression occurred? So I'm going to break this down into sort of like an animation frame. I'm going to say, here is, there's my ground. Here is block 1. Here's block 1 right there. And here's block 1 right at the moment it's making contact with block 2. So here's block 2 right here. All right. So again, number 2 for block 2, number 1 for block 1. Initial contact is made. They're stuck together. And then these 2 masses basically become a single mass, and they compress the spring because they're a single mass, and they, in essence, travel down this floor, this track, and end up over here with the spring compressed like that. Okay, so the spring, here was the spring before, it started to compress. It looked like this, nice and loose and relaxed. And then here's the spring when it got super compressed. I'll do it here. So it's the same spring. I'm just drawing it. I'm drawing the spring. Super compressed and relaxed. This is the spring in its relaxed condition. Relaxed means it's neither compressed nor elongated. And this is my compressed spring right here. And apparently this spring is compressed such that these two blocks are temporarily motionless. And then the spring will recoil and send mass 1 and 2 down in the other direction. This is mass 2. This is mass 1. And I think what I'm going to do, because the two blocks stick together, I'm going to just sort of think of them as a single object. So right here, I think of mass 1 and 2 as a single object. And I think that's my setup. Other than maybe what I'll do over here, I'm going to draw mass 1 during its incoming, the incoming part of its trip. So mass 1 is way over here. And mass 1 is coming in from the left side, making contact with mass 2 and compressing the spring. So as far, let's do EAM. This seems to me to be an EAM situation. EAM, which means you have to do all of the EAM things, energy analysis method. I'm going to call this energy state A, let me get a different color. I'm going to call this energy state A, energy state B, and energy state C. Let me move this down. This is energy state C, energy state B. And I'm doing this not because I have any special learned secrets. I'm just saying, hey, it seems to be three separate segments of this situation. All right, so now I'm going to do EAM. I need to establish a baseline, and that's kind of natural enough. This is my baseline. That is an EAM requirement. That's good to know. And now should I do to find, where's my $sign living? My $sign is living when the blocks momentarily stop. By what distance is the spring compressed? All right, so this is the amount of spring compression right here. My spring compression is indicated by this. Try that again. Hang on. I think I got a reset. Okay. I think what happens is sometimes I'm writing too fast and overloads. All right, so my spring compression is between these green lines from there to there. Okay. That's it. This is my spring compression right here. From there to there. This is what I gotta find that purple line distance. Okay, and I'm just gonna call this X, I guess. X. This is what I'm after. That's my $sign. Okay, so I guess I'm just gonna use B and C. And if I run out of ideas, then I'll try different intervals. But I'm gonna say whatever energy I have at state B plus whatever non-conservative work happens between state B and state C is the amount of energy I have at state C. So let's just go ahead and process this. This is sort of business as usual. Energy state B. This is energy state B. I might have some kinetic energy. I might have some gravitational potential energy. I might have some elastic potential energy, also known as spring energy at B. And then whatever non-conservative forces add or steal energy, that's going to equal the kinetic energy I have at C plus the gravitational potential energy at C plus the elastic potential energy at C, the spring energy. There is some low-hanging fruit here. The low-hanging fruit is as follows. If block 1 and 2, if the combined block 1 and 2, and again, why are they combined? They are combined because it's a perfectly inelastic collision. So the way to think about it is they latch on to each other. Maybe they would normally bounce off each other, but the bounce doesn't happen because there's a clasping mechanism, a docking mechanism. All right, so they compress the spring, and when the blocks momentarily stop, so that's this, K sub C is 0. There's no mention of friction, or there's no mention of anything. And again, remember this term WNC, it could be a force that's adding or stealing energy. So far, I think we've almost always dealt with a situation where a force was stealing energy, but don't get too committed to that. What if on exam 3, you had a non-conservative, or even on exam 2, you had an outside force that was actually adding energy, like a rocket pack or a tow rope or a gust of wind? This is equal to 0 because when the system is in state B, there's no spring compression. And you know what? These two offset. UGB offsets with UGC because they are one and the same. So I could just say UGB equals UGC and maybe just call it UG. So I have a UG term here that basically offsets with this UG term here. And even if you didn't like that, you could also say UGB is MGHB equals 0 because of my baseline. At this baseline right here, H subscript A equals H subscript B equals H subscript C equals 0. All right. So things have gotten very simple very quickly. Number 3, this is what I'm left with. 1/2 mv squared v. I better use subscripts. I'm going to do 1/2. I'm going to do M12 because mass 1 and mass 2 are combined. So 1/2 mv squared is more specifically 1/2 mass of 1, 2 times v at B squared. That looks good. Equals, and I guess this really did get pretty simple. 1/2 K XC. I really do like having my subscripts be super consistent. I'm going to just add this. This is X subscript C. So again, these subscripts are very helpful in terms of keeping things organized. So look how easy this seems to be. Let's just clear some more low-hanging fruit. 1/2 here cancels with 1/2 here. Here's my dollar sign. But I can tell right now there's an uh-oh. What's VB squared? This is uh-oh. What's this? I don't know. So I don't know what VB squared is. VB squared is descriptively, let's just make a little note. VB is the velocity of M1 and M2. The velocity of M1 plus M2 once they're stuck together. Once they are stuck together. We can find that. We can find that using conservation of momentum. All right, so number 5. Number 5, we just do some momentum considerations. Number 5 says, well, okay, here's conservation of momentum. Delta P equals 0 equals conservation of linear momentum. This is in the Hall of Fame. conservation of linear momentum, like Newton's second law and the work kinetic energy theorem. Those are Hall of Fame expressions. Conservation of linear momentum. And these conservation laws are great because your job then becomes keeping track of what's going on before the encounter and what's happening after the encounter. So if delta P equals 0, and I'm just going to say this, delta P equals 0 if no external, got to stress this word, if no external forces rear their ugly faces, their ugly heads. If there are no external forces, momentum is always conserved. But then you could rightly push back. You could say, well, Chris, right here, right when block 1 makes contact with block 2, block 1 smashes into block 2, and there's certainly going to be a force that exists between 1 and 2. So this is what that would look like. This would be the force. This would be the force acting on what? On 1 from 2. This would be the force acting F. This would be the force acting on 2 from 1. Right here, this is F on 2 from 1. So in this case, F12 is equal to F21 because of Newton's third law. So these are considered internal forces, and not external, internal forces. And we can ignore those. We can ignore those because whatever they are, they cancel. Whatever the leftward direction is of F12, it's exactly the same as the rightward direction of F21, thanks to Newton's third law. So these cancel. And if they cancel, they're not going to affect momentum. On the other hand, if I had a gust of wind, if all of a sudden there was a huge gust of wind that cropped up, then momentum wouldn't be conserved either. So anyway, wanted to really kind of cover that in detail because you need to know when momentum is conserved and when it's not conserved. Okay, so number 6. Let's just keep going with this. Delta P is equal to 0, and we know delta P is P final minus P initial, and we know P final is going to be mass of 1, 2 times V, I'll just go generically, VXF final, minus the initial momentum. It's, oh, actually, let me be, here's the initial momentum, M1 times VX initial. So careful, I almost was going to go off the deep end. This is delta P, this is final. This is my final momentum. The final momentum is the momentum of block 1 and 2 once they join together. Before that impact, this is my initial momentum. It was just M1 traveling down the track. M2 was just sitting there motionless. That's why you don't see M2, you just see M1. There is no M2 because it's just sitting there motionless. So if you look at step 6, I can go from step 6 to step 7 and basically say VX final, VX final equals M1 VX initial all over M12. Okay. And this is actually what we need. This VX final, I'm going to go here, number 8. Aha. This VX final that I just wrote down, this VX final equals VB. And this is where you have to have things clearly worded. This is why it's really important to explain yourself. Otherwise, it's easy for you to get lost. And even if you weren't lost, it's easy for me to get lost if I'm grading your work. This VX final right here, this represents the velocity. This is the velocity. This is the velocity of M1 plus m2. So the velocity of m1, m2 right after the collision then becomes the velocity at energy state B. So I've spent a lot of time talking about this because this is tricky. And again, it's easy enough to understand once you think on it, but you have to explain yourself so that you can be followed. Your rationale can be followed. All right, so number 9. Let's get a value for VB. Well, okay. VB equals M1. The value of M1 for me is 1.4 kg times Vx initial. M1 has an incoming velocity of 6 meters per second. 6 meters per second. That's my numerator. My denominator is M12, which is the combined mass of mass 1 and mass 2. So this would be 1.8 for mass 2. Mass 1 is 1.4. They share a unit of kilograms. So my blocks, my combined mass 1 and mass 2, immediately after impact, have a velocity of 1.4 times 6 divided by 3.2, or 2.625. 2.625 meters per second. So I think we're kind of done. Go back to 3. Go back to step number 3, because now I know everything. And solve for x subscript c, and do dimensional analysis. Okay, let's do that. All right. 0.3248. Number 11, I get, this is the amount of spring compression, 0.3248 meters. I am going to do dimensional analysis. All right, so here's the dimensional analysis. From number 3, number 3 basically says x subscript c equals mass of 1, 2 times VB squared all over K. So from a dimensional point of view, mass is expressed in terms of kilograms. Velocity is meters per second. So if I square that, I go from meters per second to meters squared over seconds squared. And in that denominator, K is the spring stiffness constant, which is newtons over meter. So do I actually get meters out of all this? I can't see it yet. I'm just going to keep going. I'm going to have kilograms, meters per second squared times meters. That's my numerator. Kilograms, meters per second squared times meters. That's my numerator. This is my denominator. Newtons per meter. And a kilogram meter per second squared. This whole thing is a Newton. So that Newton cancels with this Newton. And I do end up with meters squared. And I needed to take the square root of that, just like here. I needed to show that I'm taking a square root of this and a square root. So I just left off that square root sign. But I do get meters. Hugely helpful to do dimensional analysis. That's our second problem. Moving along. Did somebody have a question? I heard somebody.
Hello?
Yep.
I don't know like what I'm doing wrong. I've done it like 4 times and I keep getting the same answer. I solve for VB And I mean, after that, it seemed pretty easy. Just plug it back into the
What
equation.
was what was the mass of your, did you take the square root?
Yeah, or I did VB
And
M12 times VB squared.
yeah. And then whatever, okay. M12
And
times.
I divided that by
Oh,
K.
oh, I made a mistake. Here, let me do some error correction. 1/2 K x squared. This is the elastic potential energy of a spring. So I forgot to write down that. I wrote it down. I guess I knew about it because I was taking the square roots here, but that's probably what's messing you up, is my failure to write down that number 2. So try that.
All right, we're all good.
All right. Yeah, you guys. It was interesting. I had a class this morning, and for whatever reason, I was making a lot of mistakes, much like now. But it was kind of cool because I basically said, "Hey, you guys, you got to figure out where my mistake. I made a silly mistake somewhere. You find it out. So just always assume I'm making a mistake." And you might think, "Hey, Chris, how can you receive a paycheck knowing you're making a ton of mistakes?" And the answer is, I just do. So, but just assume, you guys, just assume that I'm always making a mistake. That's just a healthy outlook to have. Plus, it means you're really kind of locked in. Instead of just punching in your numbers like an automaton, you're actually thinking. It's the difference between thinking and just going sort of unconsciously through it. So, and I think I mentioned, I remember I had an instructor, I think it was for a math class or something. And she said, I'm always going to intentionally make a mistake. I don't think I need to intentionally make a mistake because they kind of just crop up naturally for me. But just every time I write down something, let's say, hey, is that really right? All right. So having said that, having sensitized you to checking for mistakes, let me get the next quiz ready. This is chapter 9, quiz 3. It's now 1:53. Okay. So if I played my cards right, you can now see chapter 9, quiz 3, which is homework problem 68. Okay. So this is, right away, I'm thinking energy analysis. Just because you can see, I can see friction, I can see gravitational potential energy, I can see kinetic energy. You can just look at that visual and see all of those things really without even thinking. Friction is non-conservative work, and kinetic energy, because it looks like block 1's going to go sliding down that ramp and smack into block 2. So that's my going in position. Again, I believe this is an energy analysis problem. And that somewhere, maybe I'll have to invoke momentum or force analysis, but I'm starting off with EAM. I'm going to call this energy state A. Energy state A is block 1 sitting up there. Block 1 then slides down this ramp. It's frictionless and collides with the stationary block 2. So I'm going to draw kind of like the last problem. Here's block 1 and block 2, just as they make contact with each other. So that's block 1 that I will move into position. Okay, there's block 1. The moment it makes contact with block 2, I'm going to call that energy state B. And then block 1 and block 2, are they stuck together? Oh, we actually have two situations. What if it's elastic? What if it's completely inelastic? So I'm going to start with A. If this is elastic, that means during the collision, no kinetic energy is lost. Of course, momentum is conserved because there are no external forces. So block 2 is going to go skidding onto that friction pad. So right here, block 2 is just comes to a rest somewhere on this rough patch. Okay, like that. All right, and that is what I'm thinking of, energy state C. All right, so, and then there's a distance. The distance traveled by block 2, we have to show vectors. This is all part of the EAM recipe. Block 2 is going to go displacing from there to there. So I'm going to call this displacement X. This is my displacement vector, X. And I guess that's my displacement vector. And they're saying D is the distance. So I would say this, the magnitude of this displacement vector equals D. Okay, just to be consistent with the problem statement. All right, so I need to know, if I just think through this, I need to know if I'm going to do EAM, I'm just thinking I need to find M2's velocity. Find M2's velocity due to M1 crashing into it. Okay. And I guess that's where momentum is going to come from. Because in your green sheets, you actually have this situation addressed in enough detail. Here's the green sheets. I'm going to focus specifically on a section right here. There's an entire section called time to derive the expression for a perfectly elastic collision. And that's what we're dealing with. So look at this horrendous amount of content. And so this is nothing more than basically algebra. The only physics that's part of this is saying, hey, if it's perfectly elastic, kinetic energy is equal to 0. So this statement right here that I'm highlighting, along with this statement, these are the only two physics statements that are involved. There's no change in momentum. That's conservation of linear momentum. And there's no change in kinetic energy if this is a perfectly elastic collision. Other than these two highlighted expressions here, everything else is just algebra rearranging. And then I finally get to box 8. Okay, so I'm just going to take a little picture of box 8. You should actually live through the algebra. It's good. It's good. It's good for you. Like cough syrup might not taste good, but it's good for you. Although I've always liked the taste of cough syrup, but that's just me. This is the velocity. So right here, this is telling you, this is actually, we don't even have to change the subscripts around too much. This is saying the velocity. So this is M2. This is the M2's velocity. This is M2's velocity after M1 crashes into it again. And this is what we need to find out, crashes into it. The only thing is, when we find the velocity of block 2 after M1 smashes into it, we have to know the incoming velocity. This is the M1 incoming velocity. And this is where EAM comes in. Okay, so we can find that. Number 2, the energy at state A plus the non-conservative work that happens between A and B equals whatever you end up with at B.
Well, Professor.
Yep.
Your screen is still showing the green sheet
Okay. Yep.
information.
Okay, thank you. So I have the kinetic energy at A plus the gravitational potential energy at A plus non-conservative work equals the energy at energy state B, the kinetic energy at state B plus gravitational potential energy at B. There's no spring, so I'm not going to write down anything to do with springs. I have to specify a baseline. This is my baseline. At this baseline, H subscript B equals H subscript C equals 0. It's basically just saying, hey, this height at B is equal to this height at C, and they're both going to be equal to 0. So I'm just focusing on what's going on between energy state A and energy state B, because that will tell me the impact velocity, the velocity with which M1 smacks into M2. All right. So what do I know? Is this, it's release from rest. So if this is release from rest, that's equal to 0. That's release from rest. There is no friction during this segment. There's friction from B to C, but from A to B, there's no friction. And these two terms, this term doesn't equal 0. This term equals 0. This term equals 0. I guess that's it. And my dollar sign is going to live in here, I think. All right. So to keep going with my energy analysis, MGHA, and I got to worry about subscripts. This is M1 GHA equals the kinetic energy 1/2 M1 VB squared. That's what I get from step 2. Step 2 basically says, okay, here's my gravitational potential energy of M1 at state A. Here's the kinetic energy of M1 at state B right before it makes contact with block 2. So that's the stipulation. Find M2's velocity due to M1 crashing into it. And so right now I'm focusing on this. I'm finding M1, the M1 incoming velocity, the velocity with which it strikes M2. Or you can see that mass cancels. And so I get in step 4, I found it. Step 4 says VB, which is equal to this V1 incoming right here. This is the same as VB. So the hardest things we're dealing with is just keeping track, because what turns out to be, or what ends up as a final result for one segment becomes the initial input for the next segment. So that takes a lot of organization. And I'm going to get equals the square root of 2GHA. Okay. And I shouldn't, yeah, let me make this clear. I didn't mean to cross out the 1/2. It should have been the M. So I'm just going to put that in my calculator memory location. I'm going to take 2 times 9.8 times HA. HA for me is 2 square root, and whatever that is, store alpha A. So that's just sitting there in calculator memory location A. I'm just going to redo it. 2 times 9.8 times 2 square root minus alpha A. Okay. So let's keep going. Number 5. Number 5. So M2's velocity resulting, and M2 is sitting there at rest. It was a stationary target. That's why we can use this expression. The stipulation is M2 is sitting there perfectly at rest, like a stationary target, like a, like an 8 ball that you're hitting with a cue ball. So M2's velocity resulting from collision with M1 is this. V2 final, which is going to be the same as the velocity at B, is going to equal 2m1, 2 times m1. My m1 value is, I don't know, so I'm just going to write it down as m1. There's 2m1. There's my numerator. My denominator is m1, which I don't know, so I'm just going to write it down as m1 plus m2. And for me, the value of m2 is just 4m1. And that is my answer as soon as I multiply it by memory location A. And I need to update something here. I need to go back here. This is the incoming velocity VB. Yeah, let me change. I need to do a little bit of cleanup. Cleanup on aisle 9. This is not VB. I'm just going to call this V incoming. So step number 4 is just the incoming velocity of M1, which is what this is. So again, I don't want to refer to this as the velocity of B. That actually is technically incorrect and confusing. So I'm just tightening up my note taking here. And once again, V2F, this is right. V2F is my velocity at B. So I'm spending most of my time just worrying about keeping things organized, which is typical. All right, so 2 times M1 over M1 plus M2 times, this is good, I think. So let's get an answer on all of this. This will be the velocity of block 2 as it heads off onto the friction patch. 2 times alpha A. Okay. I'm going to call this alpha B. Store alpha B. So let me redo that just to be sure. Minus alpha B. All right, I'm getting the same answer twice. So I know now. Let me just make a little note to self. Aha. I now know M2's velocity after impact with M1. Okay. And now I can figure out how long does it take this block to skid to a stop. Okay, step 8. Step 8, EAM again. I'm going to do EAM between B and C. The energy at B plus the non-conservative work that happens, and there is non-conservative work, equals the energy at state C. Number 9, let's blow this up. At energy state B, I could have some kinetic energy. I could have some gravitational potential energy. I could have some spring energy, but I'm not going to write it down because there's no springs. Plus WNC equals the energy at C, KC, plus UGC. There's some low-hanging fruit here. This skids to a stop. So this is going to be equal to 0. Because that friction steals all of that kinetic energy. Block 2 will come to a rest. There's no potential energy because it's sitting there at baseline level. KB, this is equal to 0. All right, so here's what I have now. Step number 10. Step number 10, kinetic energy at B is 1/2 mv squared, but I got to be really careful with subscripts. 1/2 mvb squared. And I just want to make sure my velocity at energy state B is in fact shown here which is the final. Yeah, this is right. All right. So this is, again, very easy to get lost, but that's what double and triple checking and quadruple checking does for you. All right. That's the left side. 1/2 mv squared. Oh, plus the work due to friction. So standard. Let's do magnitude angle format, F dx cosine theta. That is the left side. That's the left side of my expression. And what's it equal? The right side is just equal to 0. Okay. So I'm going to move this over just a bit. All right. Theta equals, what's theta? Well, theta is the angle between these neighbors. Theta is the angle between this displacement vector and this force vector. I have my displacement vector displayed. My force vector, as block 2 goes skidding across that friction patch, this is the kinetic friction. I'll just draw it like abnormally large. This is my kinetic friction vector, F sub K. So you can see the angle between my force vector and my displacement vector, which you have to worry about, both of those. You always need to specify force and displacement vectors, but this angle is 180. This is 180 degrees. That's what theta equals. This is why you know that energy is being stolen, because the cosine of 180 is 1. All right. Number 11. Let's keep going. Number 11. 1/2 m2 vb squared. And then here's my integral plus mu sub k mg dx cosine of 180 equals 0. Move that over. Okay, so a word about this, and I might have to do a sidebar. Where did this come from? Well, let's see. mg, this is F sub n. So if I do mu sub k times F sub n, I know kinetic friction force is equal to mu k times F sub n. That's what I'm dealing with right here. Here's my friction force expanded a bit. My friction force is mu sub k times F sub n. And then you might say, hey, Chris, shouldn't you really do a Y force inventory for block 2? And I guess I will. So if I can do this quickly. If I do a Y force inventory for block 2, here's my free body diagram. I have the normal force going up, and I have the weight force going down. And you can tell, even before I do anything else, you can tell that this upward force is the same as the downward force. So you might be tempted to fast track it. But what if this was on a ramp? That would be a great variation. Everything's the same, except instead of being a flat friction patch, it angles upward. That would be a very reasonable variation. This is M2G. This is F sub N. And then you're going to do a sum of all Y forces equals F sub N because it's going up minus mg because it's going down. Mass times acceleration. And the next thing you do is say something about acceleration. And you're saying acceleration is 0, Chris, because M2 never leaves the surface. There is never any plus or minus Y motion if we assume M2 remains flat on the surface. So this is how you're getting step C. The normal force equals the weight force. Okay, so is everything else intact? This equals 0. And then the only thing I have to worry about are my limits of integration. This M2, block M2 starts right here. It starts at 0. and it goes all the way to here, which is, I guess I'll call this D. D. Okay. And remember, when you specify the boundary conditions, let cosine of the angle figure out the positive or negative aspect. You just put the lower value displacement here, 0, and the upper value displacement here, D. Just be consistent. Once again, let cosine take care of the plus or minus aspect. Okay, and I see I forgot a subscript. This is mu sub k. This should be an M2. So this needs to be M2. Let me erase that. We can't have that. Mu sub k times M2. There. Okay, so number 12. Execute step 11 completely and then solve for D. Solve for D, and I can't help but notice the time. It's 2:16. See you at 2:25. Yeah, that sounds good. See you at 2:25. Okay. Is that right? 2:17 plus 9, 2:26. 2:26. Nice 9-minute break. Okay, we're back. Chapter 9, quiz 4. Chapter 9, quiz 4 is a different kind of collision. This is referred to as a glancing, two-dimensional, perfectly elastic collision. That's the name of it. A glancing, two-dimensional, perfectly elastic collision. And you might think, boy, this sounds like very narrowly applicable. Like how many things are glancing two-dimensional collisions? And it turns out a lot of things, glancing 2D, perfectly elastic collision. It turns out there are a ton of things in theoretical, ranging from theoretical physics to everyday testing techniques that involve particles glancing off each other, glancing two-dimensional, perfectly elastic collision. So this is, even though it's kind of densely worded, it's a pretty common situation. All right, so here, this is called scattering. This is a common technique to analyze materials. You can use this if you're a nuclear engineer working in some exotic lab, or if you're a test engineer working for DTE. You would use scattering to really figure out if a material is has integrity, if a material is holding up under the wear and tear, because this lets you study things at a very microscopic level. So here we have an alpha particle. So let's talk about chemistry for a minute. An alpha particle is what happens when you take a helium atom and you strip off its electrons. If you take a helium atom and you strip off its electrons, you end up with 2 protons plus 2 neutrons and no electrons. So if you add up the mass of 2 protons and 2 neutrons, you basically have 4, and here's a brand new unit, 4 Daltons. And I think this is the only time we see this unit. So I'm not going to make a big deal about what a Dalton is. The name is Dalton, named after a physics person from old school days. And U, it's abbreviated U. So this means all the same thing. Let me just say this again. An alpha particle is what happens when you strip the electrons off a helium atom. So 2 protons plus 2 neutrons equals 4 Daltons, or 4U for short. Because in the case of this calculation, we're basically saying the mass of a proton is approximately equal to the mass of a neutron, even though they're different. A neutron is heavier than a proton, but this is what's going on with an alpha particle. And this is my alpha particle. So I'm using it like a projectile, like a missile. I'm firing this projectile M1, which is a alpha particle, at this sitting duck, this stationary target M2. M2 is an oxygen. What's it say? Oxygen nucleus. So this is an oxygen nucleus, chemical symbol O for oxygen. An oxygen nucleus has 8 protons plus 8 neutrons equals 16 Daltons, or just 16U for short. And again, this is a stationary target. And you can approximate any collision as having a stationary target. Let's say, for example, M2 might really have a velocity going this way of 6 meters per second, and M1 has a velocity going this way of 10 meters per second. Basically, you could just say, well, I'm going to call this 0, and I'm going to call this 16. And you would, actually, I'm sorry. Yeah, I'm going to call this 0, and I would call this 4. 10 minus 6 is 4 meters per second. So you can always re-engineer these situations so that one of these particles, even though it might be moving, can be considered a stationary target. Okay, so we're firing an alpha particle at an oxygen nuclei, which you might do for a number of reasons, experimental or analysis. Okay, so the question is, knowing what we know about all of this, what's the final and initial speed of the alpha particle? So the dollar sign is, what's a good way? Final V final alpha particle, which is particle number 1, is a dollar sign. That's the final velocity of particle number 1, which is the alpha particle. And what's the initial? V initial of particle 1 is the other dollar sign. Okay, so this is clearly a job for a momentum table, an XY vector table. All right, this is made to order. All right, we've done this before. You've used these XY tables before. Anytime you have 2-dimensional vectors, this is a natural approach to take. Let's talk about the initial momentum of particle A. And I think what I'm going to do, just to be consistent, instead of particle A, I'm going to call this particle 1 initial, particle 2 initial, and this would be particle 1 final, and this would be particle 2 final. So just doing some name changing here just to be consistent. All right, so here is the initial momentum of particle 1. It looks just like this. It's coming straight this way. So this is my velocity. This is my momentum vector for M1. And again, here's M1 right there. This is the alpha particle that you're firing at the oxygen nucleus. That's my vector drawing. So here, well, let me start with the easy one. Here's my y component, 0. Here's my x component. Momentum is mass times velocity. So I just got to do mass times velocity, but as always the case, I need to worry about subscripts. This is the mass of particle 1 times the velocity of particle 1 initial, V initial of particle 1. Okay, and I'm done. I'm done with the momentum of particle 1. Here's the momentum of particle 2, 0 for x, 0 for y. So that was certainly easy, and that's because it's a stationary target. The oxygen nuclei is just sitting there like a sitting duck. It's a stationary target. So what is my total momentum before the collision? It is M1 times V1 initial. Which is that there's my dollar sign, and then this is 0. Okay. So let's do the same thing for the momentum after the collision. After the collision, this is what's happening. I've got, let's talk about particle 1. Particle 1 goes flying off at some angle like this, as shown. All right, it's flying off at some angle. Oop, didn't mean to show it there. Particle 1 is going flying off. It ricochets off. So again, it looks like a game of pool. All right. This is P final for particle 1. All right, so my x component, I got to componentize because I have a two-dimensional vector, which means I have to decompose it. This is the x component. This is the y component. That's the x component. Hang on. This is the y component. Okay, I'm going to label these things. I mentioned this before. So much of these problems, it just is based on coughing up a right angle triangle. All right, this is V final. I guess I'll call this V final 1y. This is V final 1x. Okay, so I just decomposed. I took this final velocity and I broke it down into its x component and its y component. That's all I did. So here's the x component for this particle. It would be mass times velocity. So I am talking about mass of particle 1, and this would be the final velocity, V final 1 times cos theta. And let's check the trig on that. I'll just do a little trig thing here on this triangle. I'm saying, well, what is the cosine of theta? The cosine of theta is that adjacent leg, V final 1x, over the hypotenuse, V final 1. So that's why I'm saying V final 1x equals V final 1 times cos theta. These subscripts are kind of getting out of hand, and even that needs a subscript. All right, so that looks good. Similarly, this is going to be M1 V final 1 sine theta, because that sine theta captures this y component, but it's going in the negative direction. So I'm responsible for that. I'm just going to add that negative right there. What's going on with particle 2? I gotta draw my components for particle 2. This is the x component of particle 2 after the collision, right there. This is the y component. Okay. And this is the hypotenuse. And let's label those just to keep things clear with all these subscripts. All right, this is V final of particle 2 in the y direction. This is V final particle 2 in the x direction, it's theta 2. This is V. So I know I'll just do, what is sine of theta 2? The sine of theta 2 is side opposite V final 2 y, all over hypotenuse V final 2. What is cosine of theta 2? V final 2 x over V final 2. So hopefully that's becoming kind of very apparent. So from the x component, I should draw the vector too. This is what the vector is looking like. Particle 2, which is my oxygen nuclei, goes off in that direction. Okay. So I need to capture the x and y components, and I'm now in a good position to do that with all of this prep work ready. This is going to be M2 V final 2 cos theta 2. And I guess as long as this should be theta 1 and that should be theta 1. That would be a catastrophic mistake. And then this would be, the y component is M2 V final 2 sine theta 2. All right, I'm done. So I'm going to add them all up. I'm going to add up these two x components. What do I get? M1 V final 1 cos theta 1 plus M2 V final 2 cos theta 2. I'm going to add up these two components. When I add them all up, I get just minus M1 V final 1 sine theta 1 plus M2 V final 2 sine theta 2. All right. So lots of heavy lifting in terms of the setup. So this is what conservation of linear momentum says. It says, hey, whatever you have here for the x component, whatever x momentum I have before the collision must equal the x momentum I have after the collision. And that is, again, thanks to conservation of linear momentum. And this is, again, the easy way of saying conservation of momentum. Delta P equals 0. Similarly, for the y components, same story. Whatever momentum I had here before the collision, it has to equal this momentum after the collision, because momentum is conserved. So now we can use this. I'm actually going to start with the y column. This y column catches my eye just because there's less content here. I can do 0. I'm going to start with the y column. Start with y column because my initial y momentum is 0, which means that seems like an easier path to take starting off. So I'm going to say initial y is 0. I have 0 equals minus M1 V final 1 sine theta 1 plus M2 V final 2 sine theta 2. And here's my dollar sign. So I might be done with part A pretty much now. V final 1. This is my dollar sign because this is part A. V final. Technically, this is part A. This is part A. So there it is. So here's the question. Do you know M1? Yes. Do you know theta 1? Yes. Do you know M2? Yep. You do know the final. You know VF2. That's given to you. For me, it's 160,000 meters per second. And I know theta 2. So maybe one more step with some numbers plugged in. So I have 0 equals minus M1, which is 4 Daltons. That's that alpha particle, times VF1. That's my dollar sign. VF1 times sine of theta 1. Theta 1 for me is given as 59.6 degrees plus M2, which is the oxygen nucleus, which has a mass of 16U times VF2. VF2 is basically the velocity of the oxygen nuclei after it's impacted with M1. And for me, that number is 1.6 e to the fifth. 1.6 times 10 to the fifth meters per second times sine theta 2. And for me, theta 2 is 54 degrees. Okay. Okay. So let's do this. Solve for V final of particle 1. Well, let's do that. All right. I just remembered I didn't do part B of that last problem. We will circle back. 600,304 meters per second. That's the answer to part A. So we now know the final velocity of this alpha particle. What's the initial velocity of the alpha particle? For that, I'm going to look at the X data table, the X column. Number 4, look at X. Look at X column. If I look at the X column, I have the following. I have my initial velocity. My initial velocity is M1 V initial of 1. That's my initial X momentum. Here's my final X momentum. Again, on the left side, my initial X momentum. On the right side, my final X momentum. M1, just copying it from my table, M1 V final 1, which is my dollar sign. No, I already figured out V final 1, so that's known. Cos theta 1 plus M2 VF2 cos theta 2. Okay, so with numbers, M1 is 4U. The velocity of 1 is my dollar. There's my dollar sign. V initial of particle 1. That's my dollar sign. Equals the right side is M1, which is 4U, times V final 1, which is sitting here in calculator memory location A. So I'm going to store this in calculator memory location A before I forget. Store alpha A. Okay. M1 V final 1 cosine of theta 1. Cosine of theta 1 is 59.6 degrees plus M2, which is 16U times VF2 which I know that's that 160, 1.6 e to the 5 meters per second. So I know the recoil velocity of the oxygen nuclei times cosine of theta 2. And for me, theta 2 is 54 degrees. So I think that's good. We can get, this is the dollar sign. So go ahead and solve for this variable. The initial incoming velocity of the alpha particle. Okay. All right. The initial velocity of the alpha particle is, for me, about 680,000 meters per second. So you had all this incoming velocity, and you had to give some of it. You lost some of it to the oxygen nuclei, which is why I went from 680,000 to 600,000. This is the answer to part B. Okay. So thanks to the momentum table for all of that organization. I'll get the next quiz ready. Quiz 5. Mm-hmm. I think I'll go back to the previous problem because I forgot part B, and part B won't take very long. Let me just check its deadline. I'm going to go back to quiz 3. And reopen quiz 3. All right, chapter 9, quiz 3 has been reopened. We solved for part A. And then part B says, what if the same exact thing happens, but now mass 1 and mass 2 stick together? So let me change colors. Part B, I think we're going to be able to reuse a bunch of stuff from part A. So part B, what if, am I showing what I think I'm showing? Hang on. Okay. What if M1 sticks to M2? What if M1 sticks to M2? In that case, this would be a perfectly inelastic collision. Perfectly inelastic collision. So you know what's going to change. The only thing that's going to change, instead of M2 sliding across that friction patch, M1 plus M2 slide across the friction patch, slide onto friction patch. Okay. So let's see. I'm going to look at steps 1 through 12. All right. And then just talk about what's going to change. So let's see. Number 1 says find M2's velocity due to M1 crashing into it. So I'll do it like this. I'm going to call this, let me be clever. I'm just going to call this step A, step B, and then I'll just, okay. All right. Step 1 here is just same. So there's no difference. My step 1 right here remains unchanged. Find M2's velocity due to M1 crashing into it. Well, except I guess I should change it a little bit like this. I'm going to say find the M1 plus M2 velocity. M1 comes sliding down the ramp, crashes into M2. So we need to find the M1 plus M2 velocity because they're stuck together. Number 2, that is going to be the same. Is there anything different? I don't think there's anything different about 2 because 2, I'm finding the velocity of 1 right upon impact. Number 3, same. Same. So from number 3, I still have the velocity of block 1 right before it crashes into block 2 is still going to be the square root of 2GHA. Nothing changes there. And that should be still sitting there in my calculator memory location A, but maybe I overwrote it. I'm just going to do a quick redo. 2 times 9.8 times 2 square root of that, store alpha A. Okay. All right. What about equation 4? Oh. All right. So 3 and 4 are the same. Okay. There's no difference in 2, 3, 4, 5. 5. So what is, I'll go over here with 5. Number 5. What is M2's, what is M1 plus M2 because they're stuck together velocity after collision? And it's a perfectly inelastic collision. So I'll just say number 6. Here's the new number 6. Because it's perfectly inelastic, I have mass 1 times V1 initial equals mass 1 plus mass 2 times V2 V2 final. Okay, and just a word about that. All right, so sidebar for B. Sidebar for B, I have M1, so I have P initial equals P final. And this is for segment from A to B. From A to B, from energy state A to energy state B, P initial equals P final. My initial velocity right before impact is mass of 1, V1 initial, V initial of 1. Mass 2 is just a stationary target. All of that initial velocity has to be the same as this final velocity, M1 plus M2 times the velocity of M1 plus M2 after the impact. So that's why we're saying V2 final is going to equal M1 V1 initial, which is sitting there in memory location A, all over M1 plus M2. Okay, and remember, we don't know the value of M1, so we're just going to leave it as M1. That's my numerator. My denominator is, again, M1 is unknown. M2 is 4M1, so I'm just going to factor out the M1s and cancel them. And I'm going to get an answer here, and I'm going to put this in memory location B. Okay. Store alpha B. Number 7. Same, Number 7, I know M2's velocity after impact with M1, same. I know M1 plus M2's velocity after the impact with 1. Number 8, same. Energy analysis. Number 9, same. Number 10 is going to be different. Here's number 10. All of this kinetic energy of M1 plus M2 times the velocity of those combined objects squared equal plus integral from 0 to D of mu sub k. Everything's the same here, except instead of M2, remember it's M1 plus M2 because they're stuck together. G dx cosine of 180 equals 0. And then number 11, solve for D. Okay, you can see some immediate low-hanging fruit. This M1 plus M2 term cancels with this M1 plus M2 term. Okay, so let's run the numbers. Friction. 0.45. Okay. That's the answer to part B. So it skids to a stop much more rapidly because the greater the mass, the greater the friction force. So that's one takeaway from this result. That's the answer to part B. Okay. All right. So that's part B of chapter 9, quiz 3. All right, so now we're going to chapter 9, quiz 5, I think, right? We just did quiz 4. Right, here's quiz 5. Chapter 9, quiz 5 is the same as homework problem, chapter 9, 74. Okay. So you know what? this is very much the same thing, except now we're dealing with unit vectors. Very much the same thing, or very, very similar. Very similar, except instead of angles and magnitudes, we're given unit vectors, and you should see why this is easier. I have, well, let me do it. Let me do a visual. I have two 5.1 kilogram bodies. So here's MA. This is the mass of particle A. This is particle A. Right here. Mass of particle A. And according to the givens, the velocity of particle A is provided. So let's draw that. I have an x velocity of 7 hat meters per second, and then a much greater y velocity, of 40. Maybe I'll make some adjustments here. All right, so let's label this. This is 40 meters per second j hat. This component here is 7.8 meters per second I hat. So the net velocity of particle A is this. And we would do Pythagorean theorem to find that out. But right now, this is VA. Got it. Now I have another particle B, which has the exact same mass. So you know what I think I'm going to do? Because they have the mass of particle A equals the mass of particle B. So let's just call it M. Okay. So here's particle B right here. Here's particle B. And particle B has this initial velocity. It has an x initial velocity of 8.1 meters per second, and in the I hat direction, and 2.5 meters per second in the J hat. So drawing it a little bit to scale, not like perfectly to scale, but maybe trying at least a little bit. All right, so for particle B, as mentioned, this is the mass of particle B, and they're both just going to be equal to M. All right, and then here's particle B's net velocity, like that. This was for particle B, this is 2.5 meters per second J hat. This is given as 8.1 meters per second I hat. And this is VB. So somehow these particles collide. So how would these particles collide? Maybe if I put, maybe if VB was over here, and maybe if VA, which is going much faster, was like that. I think something like this. If particle A and B had these properties, then they collide. At some point, they collide with each other. After the collision, we know what's going on with particle A. And now we need to figure out what's going on with particle B. So this is a job for collision table. And maybe I'll just say, okay, I'm going to deal with the momentum of particle A initial, and then I'm going to keep track of the momentum of particle B initial. And then I'm just going to get a total initial momentum. And then I'm going to do the same thing after the collision. After the collision, I have the momentum of particle A final, the momentum of particle B final, and just the overall net final momentum. So this is my table. All right, let's do an X component and a Y component. This is going to be the X component right here and the Y component over here. And this is going to be quite a bit easier because unit vectors, let me make a table out of this. Table, quite. All right, then I'll just copy that. Okay, so there is my quickly cobbled together table. All right, so let's just fill this in, and this is where it gets easy. All right, what's the initial momentum of particle A? Momentum is conserved, so that's what I'm banking on. The initial momentum of particle A is mass of A, so just M, because mass of A equals mass of B equals M. What's the initial X velocity? It's right here. This is the initial X velocity of particle A, 7.8. And we're going to assume meters per second. For Y, it's mass times velocity. And here's the Y velocity. It's that 40 meters per second. So this is just going to be 40. And again, I'm going to assume meters per second. What's the initial momentum for B? It's mass times velocity. So it's mass of B, which is the same as the mass of A, which is just M. What's the initial velocity of B? 8.1. Got it. That's number right there. For the Y component, it's mass times 2.5. Done. Not bad, huh? So here's the total initial momentum for X. M times 7.8 plus 8.1. For the Y, the total initial Y momentum is M times 42.5, because I can do that without a calculator. Okay, this is it. This is my total X momentum, which can't change. This is my total Y momentum, which can't change. Let's do the same thing for after the collision. After the collision, I have mass times 5.3. That's given. That's right here. This is the velocity of particle A after the collision, 5.3. And then for the Y, it's mass times 14. And for B, it's going to be the mass of B times VB final, which is one of my dollar signs. And this is, well, I better call it VB final X. And this is going to be mass times VB final Y. And when you add them all up, I get mass times 5.3 plus V. I'm just going to call it VX because we'll know what we're talking about here. And then over here, this is going to be mass times 14 plus VY. So again, I'm just going to declutter. I'm going to declutter a little bit. I'm just going to call this VX. For brevity, I'm going to call this VY. All right, so I now have the final X momentum. So this X momentum right here, this X momentum must equal this X momentum. Similarly, this Y momentum, my initial Y momentum, must remain unchanged, which means it has to equal that Y momentum. And I can just process this now. So I have my initial X momentum right there must equal my final X momentum, M times 5.3 plus Vx. And then number 2, my initial y momentum, m times 42.5, must equal my final y momentum, m times 14 plus Vy. And then solve for Vx and Vy. And then let's do part B after we get part A and B. We're doing part A and B right now. Okay, pretty easy. That's why we like unit vectors. Look how much easier this was dealing with unit vectors. Part C is actually a good question to ask because it's going to tell us just how elastic is this. Part C wants us to find the change in kinetic energy. The change in kinetic energy will equal 0 if it's perfectly elastic. So if we get a result of 0, we know what kind of collision. We know it's a perfectly elastic collision. If we get an answer that's not equal to 0, we know we've lost some energy, and it's not perfectly inelastic, but it's not perfectly elastic. It's just called elastic. I know that delta K equals 0 means K final minus K initial equals 0. So, except I have that wrong. Sorry. Let me update this. I was magically assuming there is no change. I can't say that. Part C says delta K equals $. That's better. So what I said is right. If delta K is 0, perfectly elastic. If delta K is not equal to 0, then it's just elastic. I know it can't be perfectly inelastic. So as I was saying before, I know delta K is final kinetic energy minus initial kinetic energy. All right, so let's run with that. This is what we got to find. Final kinetic energy, here goes. I better break it down because I have 2 objects. It's the final kinetic energy of A, particle A, plus the final kinetic energy of particle B. So let's just go with that. So here's the final kinetic energy of particle A, 1/2 mass of A, which is just M, times VA final, which is right here. Ooh, I don't know what VA final is. So you know what I do know? Well, I have it right here. Let's look at this picture right here. Let's look at this triangle. VA, this is VA initial. I need VA final. So I need to do another triangle. Here's particle A. And after the collision, here's my velocities. For particle A, there's my 5.3 meters per second. And here is my 14. All right, so this is given to me as 14 meters per second J hat. And this is given to me as 5.3 meters per second I hat. So what is my final velocity of particle A? Pythagorean theorem says it's right here. According to Pythagorean theorem, the final velocity of A is just going to be 14 squared plus 5.3 squared. And this will be, I'm just going to leave it. This will be VA final squared. Okay, so thanks to Pythagorean theorem for that, I can go back to step number 5. What is VA final squared? It's going to be 14 squared. We're assuming meters and seconds, and plus 5.3 squared. All right, plus 1/2 mv squared for particle B. Here's 1/2 m What's VB squared? I just found that out. I just got the X component right here and the Y component right here. So my picture for particle B, same approach. Here's the X velocity, it's 10.6. Here's the Y velocity. It was my answer to part B. That's 28.5. And then here is my velocity. So this is VB final. And this for me was 10.6 meters per second in the I hat direction. And this was 28.5 meters per second in the J hat direction. So here's that final V velocity. Ready, set, go. It's just going to be VBF squared is going to be 10.6 squared plus 28.5 squared. Okay. We know the mass. The mass is 5.1 kg. So go ahead. Let's stick this result in a calculator memory. 5.1 kg for both of them. And I'm going to just stick this in, I guess I'm just going to put in calculator memory location A. Okay. Big number, store alpha A. I'm going to redo it. Okay, I got the same answer twice, so I'm going with it. That's my final kinetic energy. Same approach for initial kinetic energy. We already have the triangle set up, so drawing time is reduced. The initial kinetic energy of particle A plus the initial kinetic energy of particle B is 1/2 m VA squared initially, and I have that right there on my screen. This is going to be 7.8 squared plus 40 squared. And let me just say a few reinforcing comments. Again, what am I doing here? This is particle A's X velocity before the collision. This is particle A's Y velocity before the collision. I'm going to use Pythagorean theorem, and Pythagorean theorem says VA squared equals 7.8 squared plus 40 squared. Okay, that's where that comes from. And then I'm going to add the initial kinetic energy of particle B, 1/2 mass, that same 5.1 or whatever your number is. And I have a number there too. It's just given. It's just, I have 8.1 squared plus 2.5 squared. And that's the answer. Let's put this in calculator memory location B. Okay. Bigger number, store alpha B. So what kind of collision am I looking at here? Number 7, change in kinetic energy, which is my $sign, is K final minus K initial. Here is K final. So I'm going to take memory location A and subtract memory location B. When I do that, calculator memory location A minus calculator memory location B for me is alpha A minus alpha B. Oops. Alpha A minus alpha B. Negative 1489.2. So, aha. Lots of kinetic energy was lost. Lots of K was lost to heat and sound. So it's not perfectly inelastic, but it's definitely not perfectly elastic. It's somewhere in between. Momentum is conserved, but in this case, kinetic energy is not conserved. So again, this is why we like unit vectors. They're just more economical. Okay. Let's do this. It's now 324. 333. See you at 333. There. Okay. 333. I think one more quiz, maybe two more, depending on where we are in the grand scheme. So that was chapter 9, quiz 5. Chapter 9, quiz 6 is next. Chapter 9, quiz 6 is next. Let me get that ready. All right. Okay, chapter 9, quiz 6 should, hang on 1 second. All right, you should see it. Chapter 9, quiz 6 should be available to you. Maybe you need to refresh. All right. Right away, I'm sensing algebra. I'm sorry, I said that completely incorrectly. Right now, I am sensing calculus for one reason right here. It's saying an object is tracked by a radar station and found to have this position vector. So this object is somehow moving according to a very specific program, a very specific function. So this is why I'm thinking calculus, just as a knee-jerk reaction, because whenever I have a function like this, a calculus, a function as you see here, I'm thinking calculus is entering my mind. Maybe not, but can't help it. All right. So this object moves very specifically according to this function, which is achieved by you, the scientist or engineer, creating a propulsion mechanism that moves according to this mathematical function. Okay. The radar station points east, its y-axis north, and its z-axis vertically up. All right, so let's draw a three-dimensional coordinate axis just to track the description here. Okay, so I have it says X is going to the right, Y is going upward, and Z is vertically up, which to us means out of the page. Okay, there's my three-dimensional coordinate axis. And it says, if the object is a 230 kilogram meteorological missile, which is basically like a weather bomb, a weather missile. So maybe we're shooting this. Maybe it's a missile that contains some sort of sensors, or maybe it's a missile that contains, I think it's silver nitrate, which is used to seed the clouds. I don't know how popular this is anymore, but at one point, there was something called cloud seeding, where you spray all this dust into a cloud, and the dust was made up of silver nitrate molecules, and it would cause rain. Basically, it would be the seeding. It would be the seed for water to form and fall out of the sky as rain. So it'd be raining silver nitrate. So I never really knew how. I don't even know if they still do it, but that used to be a practice. All right, so here is my object. Here's my missile. Okay. If the object is a 230 kilogram meteorological missile, what's the momentum? Well, all right. This could be easier than I thought. Here's the momentum. I know that momentum is equal to mass times velocity. Got it. I know, here's another thing to keep in mind, and this is in the green sheets. I know this. I know force. You guys all know that force equals mass times acceleration. So if I just want to deal with magnitudes, I'm not worrying about direction right now, but I know force is equal to MA. A is dV dt. So this is my Newton. Look what I'm doing to Newton's second law. I started out here, Newton's second law in its basic form that we're all used to. And then I said, well, let's go ahead and just write acceleration as dV dt. And then I'm thinking, well, you know what that actually looks like, because this is going to equal dP dt, because this term is catching my eye. If momentum is mass times velocity, that means change in momentum is mass times change in velocity. So this actually is a very common form of Newton's second law, dP dt. And I think we need this for part B. But there's Newton's second law using a momentum expression versus just mass and acceleration. So this is quite popular in practice. All right, so what's the momentum? Well, I got to find the velocity. If I know velocity is going to equal the time derivative of my position vector. Here's my position vector. My position vector is 3,800 minus 100 t I hat. Here's the y component of my position vector, 2940 j hat, and the z component is 240 k hat. Okay, so I need to take the time derivative of that. If I take the time derivative of that, you know what? The only thing that survives is this term with a t. So this is going to equal minus 100 t. That's the velocity, and this would have an I hat component. So just ask yourself, just sanity check. If I go through, I'm taking the time derivative of my I hat term. So hopefully you can see the derivative of 3,800 with respect to time is 0. The derivative of negative 100t with respect to time is negative 100, not negative 100t. So let me get rid of that. Negative 100 I hat meters per second. And then let's just check this. What about when I take the derivative of this j hat term? It's just a constant. There's no change in position in the j hat direction. There's no change in position in the k hat direction. If there's no change in position in those dimensions, there's no velocity in those dimensions. So that's it. This is my velocity. So now it's just a matter of P equals mv. Number three says momentum is mass times velocity. My mass is 230 kilograms, 230 kilograms times velocity, and my velocity is negative 100 meters per second in the I hat direction. So I'm getting a momentum of negative 230, negative 23,000 kilograms meters per second. Those are the units for momentum, kilograms meters per second I hat, which is why that's the I hat term. There's no velocity in the J hat direction, no velocity in the K hat direction. And you can see kilogram meter per second is the same as a Newton times second. That's the answer to 3. Pretty easy, but it's calculus, not very strenuous. What's the magnitude of the net force? Number 4. Here's the net force. I don't want the net force. I want the magnitude of the net force. I'm just going to write it like that. And I'm going to go back to this expression. The magnitude of the net force is the same as just regular F equals dP dt. Okay, so I need to take the time derivative of my momentum expression, which is right here. I need to take the time derivative of negative 23,000 kilograms meters per second I hat. And that equals 0. 0 newtons. Okay. 0 newtons. So pretty easy problem, but good because it made us use differential calculus. And to be honest, I think the biggest takeaway here is really starting to use this expression for Newton's second law, F equals ma and F equals dp dt. So you guys do this. Actually, let me run. I got to go take care of a chore that's staring right at me. I'll be back. Give me 5 minutes. So sorry for another 5-minute break. We'll do one more problem and we will actually be done early. So back in 5 minutes. Okay, one more problem. Quiz 7. Quiz 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 is 86. Let me do some shuffling. Or 9. Okay, 986. 1 second. All right, I think it's there. Chapter 9, quiz 7. Our last quiz. Okay. This is called a speed amplifier. Let me check something. Speed amplifier. Okay. Block 1 crashes into block 2. Block 2 crashes into block 3. There's no friction here, and we're undergoing one-dimensional elastic collisions with stationary targets. So you know what I'm going to do? I'm going to pull up that expression, elastic collisions with stationary targets. That was this one right here. So let me reuse this derivation provided to you in great detail in your green sheets. Okay. So part A, what's the speed and the kinetic energy? A says, are the speed, kinetic energy, and the momentum of the block greater than or the same? So this is a little bit mangled. I think for part A, they're saying, what's the block 2? I think they're saying part A, what's the velocity of M3? All right, and that, let me just double check another source to see. Chapter 9. Okay, it says, what's the speed of block 3? Okay, so our first thing we have to find out is the speed of block 3, even though mine looks mangled. I don't know if yours does. Speed of block 3. So here goes. All right. Well, let's find out. Block 1 is going to crash into block 2. Block 2 is going to repel or bounce off block 1 and crash into block 3. And then we need to find out what's the final velocity of block 3. And these are all one-dimensional elastic collisions with a stationary block 2 of 0.363 mass 1. All right. All right, so here goes. Let's do the collision. Let's look at the collision between M1 and M2. This is M2's velocity. So V, the velocity of M2 final, just sticking with this specification, is going to equal 2 times M1, and the value of M1 is just M1. That's my numerator. Here's my denominator, all over M1, which I don't know what it is, plus M2, and M2 is 0.363 M1. So I'm going to pull out that common factor of M1 and cancel it, and times the incoming velocity of M1, which is 0.239 meters per second. So I'm going to get a value, and I'm going to put that in calculator memory location A. Store alpha A. And let me do this again. So I now know the velocity at which M2 hits M3, because V2F, what I just found to be V2F, is now going to basically become V1 initial. And again, this is the tricky part, in my humble opinion. Let me just say that again, make sure I'm right. I just figured out the velocity that block 2 attains due to its collision with block 1. That's this V2 final right here. Now, when I turn the tables and I say, okay, well, now mass 2 is now crashing into mass 3, this V2 final becomes V1 initial, and this V2 final is going to be basically V3 final, and this is the dollar sign. So more than anything else, I just got to keep track of these variable names. All right, so number 2, the collision between M2 and M3. So I guess I'll do V3 final equals 2 times M2, because M2 is what's coming for it, all over M2 plus M3. I'll do it like this, times the incoming velocity of M2, which is sitting there in calculator memory location A. All right, so with one, let me peel apart these layers. The velocity of block 3 after its impact with block 2 is going to equal 2 times mass 2, which is equal to 0.363 mass 1. That's my numerator, 2 times mass 2, all over mass 2, which is 0.363 M1, plus mass 3. And mass 3 is 0.317 times mass 2, but mass 2 was 0.363 times mass 1. This could choke a horse. But I think that's it, unless I made a mistake, but I think I got it. Let me know. We'll find out. All right. And you can see the M1 is a common term that can cancel out. Okay. Meters per second. So this is definitely a velocity multiplier. M1, I mean, doesn't this seem kind of weird to you? M1 had a small velocity, but M3 magically has a greater velocity. It's as if you're getting something for nothing, but you're not. Momentum is conserved. But this is how M3 can end up with a greater velocity. It ends up with a greater velocity compared to M1, but it's momentum. How do you pay for that increase in velocity? You pay for it by a decrease in momentum, because momentum is conserved. All right, but that's good. That's our speed velocity. And then part B says, are the speed, kinetic energy, and momentum of the block greater than, less than, or the same as M1? All right, so let's see for part B. Part B says, is the speed greater? Yes, greater. The speed is greater for block. And again, I got to make sure that I'm reading this right. It says, what's the speed? Are the speed, kinetic energy, and momentum of block 3? All right, so we're looking at block 3. Does block 3 have a greater speed than M1? For part B, yes. What about part C? Part C is asking about the kinetic energy. So the kinetic energy for block 1 is equal to 1/2 M1 V1 squared equals 1/2 M1, and V1 squared is 0.239 squared. So what is that? I'm going to take 0.5 times 0.239 squared. I'm going to get basically 0.02856 M1 joules. So the kinetic energy for object 3 is 1/2 times the mass of object 3 times the velocity of object 3 squared. Let's play that out. 1/2 times the mass of object 3, which is 0.317 times the mass of object 2, and the mass of object 2 is 0.363 times the mass of object 1 times velocity squared, which was 0.532 meters per second squared. All of that, if I multiply that together, 0.5 times 0.317 times 0.363 times 0.532 squared is 0.016. So my kinetic energy actually went down 0.016 joules times M1. 0.016 M1 joules. Okay, so again, the comparison we're making here for part C. This was the kinetic energy of block 1. This is the kinetic energy of block 3. So I lost some kinetic energy to heat and sound, or certainly at least to heat. Part D says, what's the momentum? We got to compare the momenta of these two objects. So let's do P equals MV, part D. P equals MV. So for object 1, P1 equals M1 times V1. M1 is just M1. V1 is 0.239. So that's the answer. P3 equals M3 V3. M3 is equal to 0.317 times M2. And M2 is 0.363 M1. So that's my mass for 3. My velocity for 3 is this 0.532. And that equals 0.317 times 0.363 times 0.532, 0.06. 0.06 and some change times M1. So that's my momentum for particle 3. This is my momentum for particle 1. So if I look at momentum for particle 1, 0.239 times M1, for 3, 0.061 times M1. So that's why we're saying the speed of M3 increases. The kinetic energy of M3 is greater than M1, but the all right, let's see what the speed. Speed. All right, so this is speed of M3. This is comparing speed of M3. So this is V3 versus V1 is greater. This is kinetic energy. So we're comparing K1 versus K3. Kinetic energy of K3 is less than that. Here we're comparing momentum of 1 versus the momentum of 3. So yes, momentum of 3 is less than the momentum of 1 before the event, and same for kinetic energy. All right. That's good. It is now 4:06. And I think we've done 7 quizzes, which is a lot. This is almost your entire homework assignment, but make the most of it. Okay, let me just check the deadlines for everything. I think everything is pretty much due at 4:30. Let me just do a double check. Quiz 1 was due at 2 o'clock. Quiz 2 was due at 2:30. Quiz 3 is due at 4:30. Quiz 4 is due at 3. Anyway, does anyone, let me know, you guys, if